Let's say some more things about sequences. And maybe we'll even begin with a few just recall definitions. A sequence converges. What does that mean? Let's even give the name to the limit. What does that mean? All the epsilons and all the big N's.
This is probably pretty close. There exists sub n such that for n greater than big N, a of n minus a absolute value is less than epsilon for any epsilon greater than 0.
Yeah, we're going to put that for every epsilon bigger than 0. Yeah, perfect. No matter how small you want an minus a to be, you can get an minus a to be that small, as long as little n is big. What does it mean for a sequence to be Cauchy? What's the definition?
It's like the same thing, epsilon greater than 0, there exists m, n, little m, sorry,
Little m and little n, right?
Like that?
Yeah, and then I think it's, I know it's like little m greater than n, and then little n greater than n.
Should these be?
Big N. Yep. And then,
I think it's the absolute value of a n minus a n is less than epsilon. Something like that.
Cool. So there's some problems there.
Can I?
Yeah, fix it.
Okay. There exists a big N such that for all m and n bigger than n. Or, yeah.
Yeah, like that. So no matter how small you want a m and minus a n to be, you can get that difference to be that small as long as m and n are sufficiently big. Let's keep on going. What's special about Cauchy sequences?
They converge.
And it's important that it also goes the other way. So if you have a sequence that you think might converge, but you have no way of guessing the limit, and it's not monotone, then maybe try to show it's Cauchy. And let's see, one last collection of items because they will be relevant to today. What's the definition of compactness?
Xn plus 2 minus xn plus 1 is less than c of xn.
The thing is contracted. Another C1, which would naturally come after Cauchy, right? It was the next thing. So compactness was like in the topology section, right? For every open cover map count F. I'll include the of X. There's no other set, so it wasn't ambiguous. there is a finite sub-cabal. And we proved this like kind of hard theorem about compactness called the Heine-Borel theorem. What did it say? Yep, there is. And maybe I'll give you like a bit of a counterexample to like have you think. So here is an open set from 0 to 1. Let's consider the following open cabal. So let's take UK to be, gosh, can I do this 1 over k plus 2 to 1 over k? So like, there's one of the elements of this open cabal, there's another, there's another, there's another. So between the lot of them, it looks like they certainly cover the set. If I throw away all but finitely many of them, do I still cover all the set? No, there's going to be like a biggest k, right? And then, like whatever that k is, this union of the open cover is going to stop at 1 over k plus 2, which is not 0. So that's bad. So this open cover does not have a finite subcover. That set is not compact. And you'll note I took the open interval from 0 to 1. So what's the other missing word? And in fact, it's if and only if. Compact if and only if closed and bounded. Cool, so that'll be useful. That says, as soon as you know a set is closed and bounded, it's compact, so you can play this game about taking finite subcovers. That'll be relevant today. So, with that in mind, now I think I'm ready to actually talk about the stuff that's on the thing to do today. So here is what maybe is your favorite divergence sequence, -1 to the n. Just wanted to see something that like starts happening with this sequence. Let's start listing the first couple terms. So what are the terms of this sequence?
-1 and 1.
And then what's the next term?
-1.
And then what's the next term?
1.
So, without even defining what it means, so that's like a sequence of numbers that just keeps alternating between -1 and 1. Could you come up with a subsequence of that sequence which does converge? I haven't told you what a subsequence means, but like, it should be like a sequence that's contained in the sequence or something.
A sequence of 1s.
Yeah, how about just a bunch of 1s? I haven't told you what a subsequence is, but does it seem reasonable to say that that should be a subsequence of this? Yeah, you'd like take this 1, 1, take this 1, 1, take this 1, 1, take this 1, 1, dot, dot, dot. Does that seem to converge? What does its limit seem to be?
1.
Nice. So even though the sequence didn't converge, if you throw out like half of the terms, then suddenly it does. That's what we're going to study today. We're going to start studying subsequences. And a good place to begin is, what is a subsequence? Yeah.
A sequence that's a subset of another.
Yeah, but like, I'm going to write that. This is like kind of informal, and I'll say why I object. A sequence which is a subset of another. I object to this because sequences aren't sets. Right? As a set, this would just be plus and minus 1, just two numbers. So sequences aren't quite sets, but there's something like spiritually correct about that. So a subsequence, maybe here's another informal way of saying what a subsequence is. A new sequence whose terms are all terms. Let's make that legible. And in the same order that they come. So, if I gave you the sequence 1, 1/2, 1/3, 1/4. So the sequence 1 over k. Something that would not be a subsequence would be 1, 1/5, 1/4, comma, dot, 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 dot. Because 1/5 comes after 1/4. You can't swap the order. So with that in mind, I think I'm ready to state the formal definition, and then we'll see if this formal definition seems to satisfy that informal statement. So let's let f from n to n be a strictly increasing sequence of numbers. That is, for all m less than n, f of n is strictly less than f of m. Right, our definition of increasing allows for less than or equal to, so strictly increasing will require that to be a strict inequality. Let alpha from n to r be a sequence of real numbers. A sequence is a function from the natural numbers to the roots. So that's a reasonable thing to say. Then a composed with f is a subsequence of a. So let's see if that does the right thing. And I think maybe the right way to look is, oh gosh. Yeah, so let's take b sub n to be 1 over n. So the terms of that sequence are 1, 1/2, 1/3, 1/4, and so on. Let's take nk, I don't know, to be 2k plus 1. Is that a strictly increasing sequence? Oh, yeah, sorry. Is that a strictly increasing sequence? So let's think about what b sub n sub k would mean. So that means I'm going to take the rule for b and apply it to this new sequence n sub k. So b sub n sub k is 1 over 2k plus 1. And let's start listing the terms. So when k is 1, I guess that's 1 over 3. 1 over 3. Then it's 1 over 5. Then it's 1 over 7. Da, 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 da. Oh, cool. Are each of those terms of the original sequence? Are they in the same order that they show up in the original sequence? And now maybe you also see why strictly increasing is important. If f wants strictly increasing, if it just stayed constant for a while, then you could just repeat the same term of the sequence a bunch of times, which is not desirable. If it failed to be increasing at all, then suddenly the terms of the sequence would come in some random order, which is also not what we want. So, now moving a little bit further up, we'll usually write a sub n instead of a of n for sequences. In the same way, we will usually write n sub k instead of f of k. So the new notation will be a sub n sub k is a subsequence where n sub k is required to satisfy that n1 is less than n2 is less than n3 is less than n4 and so on. All right, we feeling pretty good? All right, so let's fill in some of the rest of this table. So maybe like this first row we'll talk about together. So if a sub n is negative 1 to the n, and I take the strictly increasing sequence n sub k equal to k, is that a strictly increasing sequence? Yeah, as k gets bigger, k gets bigger. So what is the formula then for a sub n sub k?
Negative 1
Negative 1
to the k.
to the k. And tell me about the limiting behavior of that thing. In that, does it converge? If so, what's the limit?
Doesn't converge.
Does not converge. And sometimes it's useful to like say what the parameter that's growing is when there's more than one. It's k that's going to infinity. Feel pretty good? How about b sub n sub k? If b sub n is the sequence 1 over n, and n sub k is k, then what's b sub n sub k?
1 over k.
Just 1 over k. Tell me about that thing's limiting behavior.
There's a limit of 0 if it goes 1 more than that.
Yeah, but I think I'm happy enough saying the limit, right? The limit doesn't care what happens for the first 5 times. Think you can fill in the rest of the table? All right. Do that. Not terrible. Okay. All right, cool. So, let's hear 'em. N sub k equal to k plus 1. What's a sub n sub k?
Negative 1 to the k plus 1.
Negative 1 to the k plus 1. I guess if you wanted to simplify that at all, that's negative 1 to the k, if you care. Does it converge?
No.
N sub k equal to 2k.
Negative 1 to the 2k.
Negative 1 to the 2k. Does that simplify at all?
Not really.
Yeah, it does.
You can do negative 1 to the 2 to the k. Yeah.
Yeah, okay. What's negative 1 to the 2?
1.
What's 1 to the k?
1.
Oh, cool. So this is just always 1. So that's like the always 1 sequence that we found above. Tell me about its limiting behavior.
1.
It converges to 1. Do people agree? Next one, 2k plus 1. What's a sub n sub k?
Negative 1 to the 2k plus 1.
Negative 1 to the 2k plus 1. How does it simplify?
Negative 1 to k. Negative parentheses 1 to k.
I think there's always negative 1. Does that agree with what you were saying?
Yeah.
Okay, I think I missed on some parentheses then. Tell me about its limiting behavior.
Negative 1.
Last one, n sub k equal to k squared.
Negative 1 to k squared.
Does that simplify at all? I mean, it does, because of special properties about negative 1. Let's start listing terms. When k equals 1, what do you get?
1. Negative 1.
When k equals 2, what do you get?
1.
When k equals 3, what do you get?
Negative 1.
Cool. Does that seem like it's the same as the original sequence? No. So this actually simplifies. This is just negative 1 to the k. Tell me about its limiting behavior.
Doesn't converge.
Nice. Next column. B sub n equal to 1 over n. When n sub k is k plus 1, what's b sub n sub k?
1 over k plus 1.
No good simplification to happen. What's the limit?
0.
In fact, let's skip filling in the third column. Tell me the rest of the entries in that last column.
0.
Converges to 0 regardless. So there's something that's suggested here if you start with something that converges, subsequences converge. Which hopefully that seems intuitively like it's reasonable. If you start with something that diverges, then subsequence, some of them converge, some of them diverge. That's the takeaway of this table. And in fact, this idea of some subsequences converge is like the big theorem of the day. But let's start with something a little bit lighter. Let's let A sub n be a sequence and A be a number. If A sub n converges to A, then every subsequence converges to A. Does that agree with what this table suggested? Yeah. And let's try to come up with a proof. All right. So let's let an be a sequence. Let A be a real number. Let's suppose that an converges to A. And now I need to consider absolutely any subsequence A sub n sub k of A. And there's a secret assumption there. N sub k has to be a strictly increasing sequence of real numbers for that to make sense. And I guess it's not so secret because it's written explicitly. And that'll be important. And oftentimes you'll be appealing in your proofs to, so n sub k is a strictly increasing sequence of real numbers. All right. So there's the setup. What is it that we need to show? Our goal is every subsequence converges to 1.
A and n sub k equals 1.
Oh, not to 1, to A. I may have said 1 though. That's probably my fault. Oh, neat. So that's like a limit statement. So we need that for every epsilon bigger than 0, there exists a big N such that for all k is the independent variable now, k bigger than big N, absolute value A sub n sub k minus A is less than epsilon. Feeling pretty good? And we know that A sub n converges, right? So what does the fact that A sub n converges tell us?
The same definition, but instead of n sub k, it's just n.
Same thing, but instead of n sub k, it's just n. So maybe, well, how brave do we feel? Do we think that that big N will be the same big N that should walk for A sub n sub k? How many people think? How many people are feeling brave? Should I call it big N or something else just in case? Big N? Something else just in case. All right. So there exists some n, let's call it n prime, such that for all n bigger than big N prime, absolute value A sub n minus A is less than epsilon. And notice I don't need to rewrite the for all epsilon bigger than 0 because I've already considered any epsilon bigger than 0 beforehand. All right, cool. So there's a logical jump here that isn't so hard to do, and in fact is going to be homework. Here is a claim. If n sub k is a strictly increasing sequence of natural numbers, then n sub k is bigger than or equal to k for every natural number k. Does that seem like believable? If you have a sequence of natural numbers that keeps strictly growing, like the slowest growing strictly increasing sequence should just be k. That seems believable. Proof up to the rear, homework. Let's use that claim. So let's now suppose that k is bigger than this big N prime and see what happens. Well, if k is bigger than big N prime, then what can you tell me about n sub k because of that claim?
Then n sub k is greater than.
Ooh, so this nk satisfies that universally quantified statement. So the conclusion follows for n sub k. So that, maybe I'll even label this with a star. So that by star, What conclusion can you make?
N sub k is greater than
Well, we already have n sub k bigger than big N prime. So, if little n is anything bigger than big N prime, then this inequality happens for that little n. Does n sub k satisfies this inequality? So it satisfies the conclusion. So what inequality can I conclude using star?
A sub n sub k is minus a plus epsilon.
Yeah. Oh, cool. Is that the conclusion that I wanted? Yeah, so in fact, what do you think? Should I go and erase those primes now? Yeah, it looks like n prime was the big N I wanted. Didn't know that before I started, but worked out that way. Oh, cool. Does that complete the proof? Oh, kind of. Haven't proven that claim, have I? That's a lot. You will do that. All right. So, if you start with a convergent sequence, every subsequence converges. So when you take a subsequence of a sequence, behavior only gets better. You can only make life better when you take a subsequence. And let's see, it's been a while since I've asked this, and I forget what the answer was. How many people have already taken the abstract algebra class, or are taking now? So this is a lot like what happens with subgroups. Subgroups become nicer when you take a subgroup. And they don't become less nice. Like you start with an abelian group, every subgroup is abelian. All right, so let's talk about this idea of subsequences which converge. There's a definition associated with it, and hopefully it's a definition that seems friendly enough. If an is a sequence and a is a number, then a is a subsequential limit of an if there is a subsequence which converges to a. That seem like a reasonable definition? Yeah. A subsequential limit is a limit of a subsequence. So, let's try to do something with that definition. Based on the stuff that's on like the previous page, a sub n equal to -1 to the n, it seems to have at least two subsequential limits. What two subsequential limits did we see?
One
and -1. There might be more. I mean, there obviously aren't. And in fact, the other homework problem for this one is there aren't. Those are the only two. But let's prove the at least bit of this. -1 to the n has at least two subsequential limits, namely 1 and -1. So let's do that. So let's let a sub n be -1 to n, and then each of their subsequences, a sub n sub k and a sub m sub k. So two different subsequences, so I better give the strictly increasing sequence you plug into the different names. Which converge to 1 and -1, respectively. And now I guess I just need to come up with some formulas for these n sub k's, but I think we have done already. So based on the previous page, or just intuition, what seems like a good choice of n sub k if I want to converge to positive?
2k.
2k. Let's try it. So let's let nk be equal to 2 times k. And you know what, I'm going to jump around a little bit. A sub n sub k, let's try to work out what that is. So, what formula do you get if you just plug in the formula for n sub k into the formula for a sub n?
-1 to 2k.
-1 to the 2k? Oh, and what is that?
-1 squared to the k.
Sure. And in fact, I'm going to skip the algebra. Like, what's the actual conclusion? What is that equal to?
1.
It's just always 1. Ooh. So, if I were to ask you to explain why that converges to 1, what would you say?
For all k, a sub n sub k equals 1.
Cool. Why does that mean the limit is 1?
Because then a sub n minus a sub n minus a sub n is equal to 0, which is less than a greater than 0.
Oh, cool. So you can come up with straight up epsilon n proof. We also had like a theorem we proved a while ago, right? You remember the unit on like limit laws? Constant sequence. We've proven that constant sequences converge. As a sub n sub k is constant. This isn't saying like what you were coming up with wouldn't walk, but it won't fit in the one line I have provided myself. So there's like half of it. If I want to get to -1 as the limit, what should I use for n sub k?
2k plus 1.
Are you at 2k plus 1? Is that the only choice that you could possibly make?
No.
No, you could like do 2k minus 1, I think, 4k plus 1, 6k plus 3. This is maybe the simplest choice. Same question then. What does a sub m sub k simplify to?
-1.
Oh, okay. So that also converges to -1 because it's a constant sequence. Yeah, people feeling pretty good so far? So, if you want to show that something is a subsequential limit, one way to do that is find a subsequence that converges to it. Let's also now get to the main result for today. So I'm going to remind you, well, we're going to state this. It was stated earlier in the book as like a definition to do some stuff with. Reformulation of subsequential limit. Let a sub n be a sequence and a be a real number, then a is a subsequential limit of a sub n if and only if however epsilon bigger than 0. And every big n is some little n bigger than big n, so that the absolute value of a sub n minus a is less than epsilon. That seemed like it should probably be the same. Right. What does it mean to be a subsequential limit? It means that I can throw out a bunch of terms, still have infinitely many. That sequence now gets really, really close to Oh, well, that means that for every epsilon, a sub n sub k is going to converge to a. So, as soon as like k is really big, a sub n sub k minus a is less than epsilon. Well, if you now consider any big n, well, eventually n sub k's are all bigger than big n because it's strictly increasing. Yeah, that seems like it should walk out. And the opposite direction is maybe a little bit harder. As long as I announce, like, reminded you that challenge problems are important, there's another one of them. And that one's not so bad to do. I just didn't want to put it in the notes for the sake of time today. People feeling good? All right. All right. The Bolzano-Weierstrass theorem. And in fact, we stated another thing that we called the Bolzano-Weierstrass theorem last time. Every infinite bounded set has a limit point. Here's the sequential analog of it. Every bounded sequence has a convergent subsequence. And let's go ahead and prove it. There's going to be some topology that happens. So, let's do it. So maybe I'll restate the theorem at the top of this page just so we don't lose the plot of what we're trying to prove. Theorem. If a sub n is a bounded sequence, then there is a convergent subsequence. Yeah, cool. All right, so let's do it. Let's let A and B be a bounded sequence. Let's let L and U be upper and lower bounds respectively. Let's suppose something for the sake of contradiction. If I want to show that there exists a convergent subsequence, then what do I get to assume? I want to show there is a convergent subsequence. Let's assume there is no convergent subsequence. Let's assume for the sake of contradiction that there is no convergent subsequence. So there is no subsequential limit. Right, because a subsequential limit would be the limit of a subsequence, but there is no convergent subsequence. So far, so good. And let's now, I stated that theorem but didn't prove it because I wanted to use it for something. So let's, bottom of the page, let's just remind ourselves of theorem 6.3.6. Remind me, what does that theorem say? I mean, y'all have it open now, so I don't.
That A and B sequence,
Mm-hmm.
and little a, b in real numbers.
Mm-hmm.
And A is a subsequential limit of A of n if and only if for every epsilon greater than 0, every big N, there is some little n bigger than big N. So that absolute value A of n minus A is less than epsilon.
Cool. So, with that down, I have assumed that there are no convergent subsequences, so there are no subsequential limits. So no number A will satisfy this condition down here. So that means that for every A, not that is true. So, indeed, for every x in between L and U, x cannot be a subsequential limit. There are no subsequential limits. So by this theorem, let's do the logical calculus, but I'm going to do it down here. So not x is a subsequential limit means not for all epsilon bigger than 0, for all big N, there exists a little n bigger than big N, such that absolute value xn minus, an minus x is the subsequential limit, is less than epsilon. And now let's go and negate that. So what do you get when you apply the logical calculus to negate that? There does not exist, that kind of means like a for all, right? Oh, and minus x. Cool. So, I'm now going to copy that over up there now that we've walked that out. So by theorem 6.3.6, I'm going to also put the for all x in L, comma U, just to remind myself that it depends on these things too. There exists an epsilon that depends on x bigger than 0. There exists a big N that depends on x, such that for all little n bigger than big N of x, absolute value an minus x is bigger than or equal to epsilon of x. Cool. So, maybe pictorially, what does that say? So, if I pick that x, and there's x minus epsilon of x, and there's x plus epsilon of x. A sub n is not in here once little n is bigger than big N of x. All right, so let's use that to do something. So there's a little open interval, right, that contains little x. Here's where compactness is going to come into play. I can put those together to get an open cover. From each x, I get a choice of epsilon. Let's take each choice of x and the corresponding choice of epsilon. So for every x in between L and U, let's set u of x to be x minus epsilon of x, x plus epsilon of x, so that for all little n bigger than big N of x, a sub n is not in u of x. I'll set f to be the collection of all of those u of x's. I claim that that's an open cover. Why is it an open cover? So to be an open cover, well, it needs to be a collection of open sets. Are each of those u of x's open?
Yeah.
Yeah, they're open intervals. If I give you an x in between L and U, can you give me a u of x that contains it?
Yes.
Yeah, in fact, it's exactly that u of x, right? So let's see, for all x, u of x is open. And for all x in LU, x is in u of x is in big F. So, big F is an open cover. Nice. Now the interval from L to U, is that closed? The closed interval from L to U, is it closed? Is it bounded? So by Heine-Borel, what do you conclude?
It's compact.
It's compact. This is an open cover of a compact set. I can throw out all but finitely many and still have a cover. So, since this thing is compact, there is a finite subcover G equal to u of x1 through u of xk. I will now consider any little n bigger than the max between n of x1, n of x2, n of xk. Let's get a contradiction. So, let's see what that contradiction will be. And maybe we'll sketch it out over here. So let's see, I know little n is bigger than this max. So little n is definitely bigger than n of xi for all I. Well, since little n is bigger than n of xi, n is bigger than n of xi, that means absolute value of an minus x is bigger than or equal to epsilon of x. Ooh, let's think pictorially about that. So an cannot be in between x minus epsilon of x to x plus epsilon of x, xi. All right. Why is that going to be a contradiction? So I've just concluded that an isn't in any of the u of x sub i's. Is an supposed to be between L and U? So it should be in that closed interval, right? But this finite subcover is a cover. So it has to be in one of them. Well, there's our contradiction. So now let's just write it up a little bit cleaner in my remaining 3 minutes. All right, well, let's see. As little n is bigger than n of x sub I for each I, let's label this as star. Nope, star is already used. Triangle. Triangle concludes absolute value of a sub n minus x sub I is bigger than or equal to epsilon of x sub I. Thus, a sub n is not in u of x sub I. Because right, u of x sub I was by definition the stuff that is within that epsilon of x sub I of x sub I. But L and U are bounds on a sub n, so a sub n is definitely in L to U. This contradicts the fact that G is a covar of L to U. All right, so we've gotten ourselves a contradiction. What can we conclude?
The thing we assume the contradiction is wrong is.
The thing we assume for the sake of contradiction is wrong. But like, I don't want to do the wrong. Negate the thing I assume for the sake of contradiction.
There is at least a convergence of sequence.
There is some convergent subsequence. And we'll see a few examples of why this is powerful. This says that if you start with any bounded sequence, that sequence itself might not converge. But as long as you're willing to take a subsequence, you can get one that converges. Yeah. And I don't know, with my remaining like less than a minute, let's just do a quick preview of what's in the homework. So I said I'd have you prove that claim. There's the statement of the claim, and in fact I've given you the proof. It's just all out of order, and I've added some extra bullet points accidentally. So you can try to come up with a proof on your own. It's not that hard to do. But if you want to try to read through these and like come up with the proof of what seems relevant where, as a hint, it's inductive. You can come up with the proof. The other one is the proof that the sequence A sub n has exactly the subsequential limits that we thought it should. So if Blackwell rule L is instead of all subsequential limits, so L is exactly the set containing -1 and 1. So I guess I need to do 2 set containments. Neato. That feel pretty okay? All right. So, Friday will be benchmark day. On Monday, we are going to introduce the concept of limits of functions and continuity of functions. And I guess last thing is you should keep unpacking. I've updated like the homework deadline policy. If there's stuff that you want to turn it in. There will be a penalty, but it won't be a huge penalty. If there's stuff that you lost some points on, and any homework problem that you got less than 70%, you can turn that in again, lost some points. I think those are the main ones. Cool. You come by Mark later today?
Yeah.
Excellent. See you there.